This is lecture 50 of Condensed Matter Physics 1. And from lecture 49, we started discussing magnetism in materials. What I did in lecture 49, I will just recap, is that I wrote the Hamiltonian for an atom in the magnetic field, and this came out to be H 0 plus Bohr magneton L plus G spin S plus Q square over 2 m A R I square summed over I, where H 0 is the spherically symmetric effective Hamiltonian for the atom. So, this is equal to summation of I minus h cross square over 2 m del I square plus summation over I some V effective R I, where V effective is taken to be central and it is a sum of the nuclear potential plus whatever the electron-electron interaction potential comes. But the main thing is there is some sort of a spherical potential, and therefore, the wave functions psi r are some r and l are y l m theta and phi, and these are eigenstates of orbital angular momentum. The total wave function with the spin is also multiplied by the spin part. So, let me write this as S. And then we used the fact that these LIs can add to give a total angular momentum summation Li, and individual S can add to give a total spin angular momentum Si, and then we wrote the Hamiltonian. Using this and perturbation theory, so that was one important thing we learned, is that I can use perturbation theory because all these extra terms are much smaller than the eigenvalues of H 0, and from that we got the diamagnetic response. And the term that was responsible for it was Q square over 2 m summation A square. All right. The second term, the first term proportional to L plus G S S, we had not treated yesterday, and that is what we are going to do today. I forgot to write dotted with B here. Yes, going back here. This term is going to give you paramagnetic response, and for that the term which is responsible is this one. Now, before I proceed further, let me just note that diamagnetic response came out to be temperature independent. Whereas the paramagnetic response that I am going to calculate will be temperature dependent. So, will be temperature dependent and will give me something called Curie's law. Now, one term you may be wondering is the second order response, because I went all the way up to B square. So, this is paramagnetic response up to taking the first order perturbation theory. If I calculate the second order response of the paramagnetic term, this also gives you a temperature independent paramagnetic response, which is known as Van Vleck paramagnetism, which I will comment upon later. Right now, let me just focus on the first order perturbation theory. So, we are looking at paramagnetic response of ions via first order perturbation theory. So, I need to calculate the expectation value with respect to some wave function, which is a combination of this was a mu b, which I did not write, dotted with b. This would give you the energy change in psi. Next question is, what psi do I take? So, that is where I am going to invoke something called the Russel-Saunders coupling. And what is responsible for it is it arises from the spin orbit interaction. So, let me explain that first. And what it does is that gives you a wave function in which we are going to work. So, I had written the Hamiltonian as h 0 plus mu b L plus G S S dot b plus the second order I am going to ignore, and there is one more term which is the spin orbit coupling term. So, some constant L dot S. So, this is spin orbit, which I had not written earlier when I was working with diamagnetic systems. And this C L dot S happens to be larger than mu b L plus G S S dot b. So, before this fellow acts, this has an effect. So, C L dot S modifies the wave function before mu b L plus G S S dot b perturbation can be applied. This happens because the L dot S coupling term is larger. So, it acts before the second term. So, in calculation I have to use this first. So, what it does is, so I'll make that basis, I'll modify the wave function accordingly, and then apply this perturbation on that. Both are treated perturbatively. So, let me make that comment, both C L dot S and this magnetic term are perturbative. It just so happens that one perturbation is larger than the other. So, I got to be very careful in which order do I use them. So, what L dot S coupling does is, given an L and given S, let me keep giving you examples. For example, if I take carbon atom, which has the shell structure 1s2, 2s2, 2p2. So, I am combining 2p electrons, they give L equals either 2, 1 or 0. They can. And similarly, if I take oxygen atom, it will give me 2, 1, 0 because I combine the whole. So, I will leave the oxygen part for you. And if I take the S value, there are 2 electrons and they can in principle give me S equals 1 or 0. So, I have these possible values. Now, L dot S coupling combines the two angular momenta L and S and give total angular momentum J. So, for example, in this case, if I have L equals 2, S equals 1, possible J values are 3, 2, 1, that is it. If I take L equals 1, S equals 1, I have J, possible values are 2, 1 and 0 and so on. So, I am just writing it in general. In fact, you will see that if you have 2 equivalent electrons, L equals 2 is not allowed in carbon, but right now I am just writing it for the sake of just adding and giving an example. Now, so once we have this L and then I get a J, what are the rules? How do we form which L to choose, which J to take? So, these are known as in general Hund's rules, and that is how I am going to fill the electrons and pick up my L and J values. So, I should write them. 1, fill atomic shells so that S is maximized. Now, Hund's rules are obviously following that the energy should be minimum. So, these rules are based on minimization of the energy consistent with Pauli exclusion principle and the orbitals being in the central field. Number 2, given a value of S, maximize L. So, you should have largest possible L values. And then third, J comes out to be from L minus S mod, then L minus S plus 1 all the way up to L plus S minus 1 and L plus S. So many J values. And which is the lowest energy? For less than half filled shells, the smallest J has lowest energy. For half filled shell, J equals S. So, for half filled shell, J equals S. So, there is no ambiguity. And finally, for more than half filled shells, largest J has the lowest energy. Let me illustrate this by examples. So, I started with carbon 1s2, 2s2, 2p6. 1s2 and 2s2 are fully occupied, so I do not really have to worry about them. 2p6 or 2p2. P has 3 different ml values. ml is +1, 0, -1. First rule says that I have to maximize the S. So, I should have 2 up spin electrons filling them. In 1 ml, I cannot have 2 up spin electrons. So, I have first one in 1 and second one in 0. Why? Because I have also invoked the second rule, that is L maximum. So, I start with the largest value, let me write this, to have L maximum, start filling largest ml and then go to decreasing ml. So, I started with ml equals 1 and then put next in ml equals 0. That way I can maximize the L value. So, in this case, since they are equivalent electrons, as I said earlier, L equals 2 is not allowed. So, largest L possible is 1 because Lz is 1 for these 2 electrons. S maximum is 1 and the possible J values are then 0, 1 and 2. What will be the lowest energy? This is less than half filled shell, because total number of electrons that can be accommodated in this are 6. There are only 2 electrons. So, lowest J value would have the smallest energy. So, ground state is going to be, this is written in the notation 2s plus 1, then the L term and J. So, in this case S is 1 and therefore, this is going to be 3, L is 1. So, it is going to be P and J is 0. That is the ground state. I will illustrate all 3 cases. Next, let us take nitrogen, which is 1s2, 2s2, 2p3. So, in this case, I have exactly half filled shell. So, if I fill the electrons, maximizing S, I am going to have 1 in ml equals +1, 0 and -1 in all these 3. So, S has been maximized, but L is 0. So, as I said earlier, if it is exactly half filled, L is 0. So, Lz total comes out to be 0, L is 0, S is 3 halves and there is no ambiguity in J. J is 3 halves. So, its ground state is going to be 2s plus 1 L j, which in this case happens to be 4, L is S, J is 3 halves. And finally, I will take the example of more than half fill, and that is oxygen. Oxygen has a shell configuration 1s2, 2s2, 2p4, and the way we fill the p orbital, S and p, 2 s orbitals are already complete. So, I do not have to worry about them. ml equals +1, 0 and -1. First, I maximize the spins. So, I put all parallel spins, they can be in these different mLs, and the fourth one would go to +1 again, because I want to maximize L. So, Once we do that, let us see what L value is going to be. So, the first 3 up spins L give L to be 0, and the last one gives Lz equals 1, and this would imply L equals 1. S, the 2 paired spins in plus ml equals plus 1 give you 0 S. So, Sz is 1, and this gives you S equals 1, and therefore, possible J values are 0, 1, and 2. Now, this is more than half filled. This has more than half filled shell. So, this implies E lowest is for J largest. So, the ground state configuration is going to be with the largest J. This is again given as 2s plus 1 Lj, and this is going to be 2s plus 1 is 3, L is P, and J is 2. That is the ground state for oxygen. So, what we learned through this is that the basis for calculations that is before we apply perturbation L plus GSS dot B mu B, the atom or the ion has states specified by J, L, S, and Jz. What this implies is that Lz and Sz are not conserved. They are not conserved because L and S are interacting. So, some part of Sz can go to Lz, some part of Lz can come to Sz, but it does it in such a manner that Jz equals Lz plus Sz is a good quantum number. And that means that it is conserved. So, the good quantum numbers that we are dealing with now are J, the total angular momentum, L, the total orbital angular momentum, S, the total spin angular momentum, and finally Jz, that is the Z component of J. Jz obviously goes from minus J to plus J. So, this is the basis we are working in, and now what I got to do is calculate the expectation value of this perturbation. So, perturbation H1 is mu B L plus GS S dot B, and if I calculate the expectation value, and therefore, the change E1 is going to be expectation value with respect to J, L, S, Jz dotted with L plus Gs S J L S Jz dotted with B, and there is a mu B here. So, we need to calculate this expectation value in the basis where the total angular momentum is satisfied. So, this is given by something called the Wigner Eckart theorem. I would like you to recall this from your quantum mechanics. In our case, we are calculating the expectation value of two vectors, and what it means in this is, if I calculate the expectation value of this vector, some vector v in this basis j, l, s, j, z, j, l, s, j, z, this will be equal to, let me give it a name, g, j, l, s. That means it will not depend on the z component of the angular momentum times the expectation value j, l, s, j, z, j vector, j, l, s, j, z. The theorem is written in various different forms, and in particular it is written for the spherical tensor of order k with the component q, but I have used a particular form that is useful for us here. So, now what I got to calculate is the expectation value of L dot B, expectation value of S dot B, and then calculate this G, J, L, S. So, let us do that now. So, if I were to calculate the expectation value of L in this basis J, L, S, J, Z, L, J, L, S, J, Z. And finally, remember I am interested in dotted with B. So, to do that, let me take this will be equal to some G whatever this expectation value J, the expectation value. Let me take the dot product of this J, L, S, J, Z, L dot J. This will give me the value of G. So, this will be J, L, S, J, Z, which will be equal to whatever some number here J dot J, and this gives me something here J, J plus 1. Now, L dot J is equal to L dot L plus L dot S. So, this gives me the expectation value for L dot L, because total angular momentum is a good quantum number, is L, L plus 1 plus L dot S. Similarly, I can do the same calculation for S, and I am going to get S dot j is equal to S plus 1 plus L dot S, and this will give me the value of that G that I had in front of the Wigner-Riccard theorem. So, let us do that now. This G J L S that I wrote, which was the J defined through J L S J Z L plus G S S J L S J Z. I want to write this finally because everything is in terms of J. Mu B, there is a mu B here, G J L S times J. And I have already calculated. So, this is what will define the what is also known as the reduced matrix element in terms of Wigner-Riccard theorem. And here, once I define it, this is in terms of the G factor for magnetic moment. So, this is also known as Lande G factor, and this is what we are calculating. So, if I take the dot product with J, I get mu B J L S J Z L dot J plus G S, which is 2 S dot J J L S J Z is equal to mu B G J L S J dot J, which is J plus 1. Mu B cancels from both sides, and I have already calculated L dot J and S dot J. So, this comes out to be L plus 1 plus G S, which is 2 S plus 1 plus 2 L dot S expectation value is equal to G J L S J plus 1. Let us see if this is correct. In the L plus 1 I had L dot S, in this I had L dot S, so there should be 3. Now, L dot S can be calculated very easily because I have J equals L plus S. So, J square is L square plus S square plus 2 L dot S. So, L dot S is equal to J square minus L square minus S square divided by 2. And if I take the expectation value of L dot S, it will come out to be J plus 1 minus L plus 1 minus S plus 1. Now, we are all set to do the calculation of GJLS, and you substitute the numbers. Substitute everything together, and let me warn you here, I may have missed a factor in front of some terms, you are going to get G J L S equals 1 plus J plus 1 minus L plus 1 plus S plus 1 divided by 2 J plus 1, which can also be written as 3 by 2 plus S plus 1 minus L plus 1 divided by 2 J plus 1. So, what this tells you is that when you did the calculation of L plus G S S in this basis of J L S J Z, you can write this equal to expectation value with respect to the same thing J L S J Z, and inside I am going to have a G factor, let me call it G L J and the rest. This follows from Wigner theorem because the expectation value of L and S both are proportional to J. Now, G L has this formula because G for orbital part of mu is equal to 1 and G for spin part is equal to 2. So, it comes somewhere in the middle. Otherwise, everything would have been just 1. So, once we have this GL factor, I am going to write the magnetic moment is going to be equal to minus mu b, because the magnetic moment for electron is in the opposite direction to the J, times this G JLS times J. And the expectation value of that term L plus GS S in this basis of J is going to be equal to J same basis times GL, and therefore J this basis L plus GS S J dotted with B is going to be equal to G this JLS J dot B same basis, and we take B in the Z direction, then everything becomes the Z component. So, let me summarize therefore. The perturbation Hamiltonian now is mu b G Lande G factor times J dot B. And therefore, when the energy is calculated, and different J Z have different energies, and they are separated by how much? Minus mu b G L J Z. So, suppose J is equal to 1, I am going to have J Z equals minus 1, Jz equals 0 and Jz equals 1 as the energy levels, that degenerate energy levels have separated, and this distance is going to be equal to mu b g, whatever Lande g factor is, times b. Similarly, if I have j equals, let us say, 5 halves, I am going to have 5 different energy levels: minus 5 by 2, minus 3 by 2, minus a half, plus a half, or 6, plus 3 by 2, and plus 5 by 2. And each one of them is going to be separated by, again, mu b g l b. So, this is how we took this Hamiltonian, which was H 0 plus, then we had this Russel-Saunders coupling, plus mu b L plus G s S dot b. This is what happens. First, the C L plus 1 term gives you these good quantum numbers. It makes new states, which are these J states with degenerate Jz levels, and then when you apply this magnetic field, those levels split. Since there is energy difference, let me make this energy difference. At a temperature T, lower energy levels are more populated than the upper ones. At finite non-zero temperature, lower levels are more populated than the upper ones. If they are more populated, that means whatever quantities they have, they are going to have more contribution than the upper levels, and that is what gives it a magnetic moment. So, let us see that. So, I have these levels. Jz equals minus j plus 1, minus j plus 2, and so on. The energy of this level is minus mu b g l j b. The corresponding magnetic moment is mu b g Lande j, and so on. The probability of occupation for this is e raised to mu b g l j z b over k b t. So, now I know everything. I can calculate whatever quantity I want to. I can calculate the free energy, by calculating the partition function, and then calculate the magnetic moment m as minus d e d f dB, or I can calculate the magnetic moment directly by writing m equals, the magnetic moment is mu b g j z for the Jz state, and then I can write e raised to minus mu b GL Jz b over kt summed over Jz equals minus j2 plus j, and divide by the total probability, which will be minus j to j sum of e raised to minus mu b GL Jz b over kBt. So, this calculation can be performed and you can get some function, but we will work in the regime and that holds for room temperature too, where mu b GL Jz b over kBt is much less than 1. In that case, the exponential can be expanded, and you can sum over, and I will leave that calculation for you. So, I will expand e raised to minus x as 1 minus x plus higher order terms, which I am going to neglect. Summation Jz equals minus j to j, 1 is going to be 2j plus 1, summation Jz equals minus j to j, Jz is going to be 0, and summation Jz equals minus j to j, Jz square is going to be equal to j plus 1, 2j plus 1 divided by 3, and you do all this calculation and you substitute and you get the magnetic moment as mu b square G Lande square j plus 1 divided by 3 kBt times b. Which I am going to write as mu b square p square over 3 kBt b, where p square is equal to GL square j plus 1, p equals GL square root of j plus 1 is the effective magneton number. It is as if this many Bohr magnetons I have in the system, and that is what it comes out to be. And the susceptibility, which is m over b, comes out to be some constant, depends on the effective magneton number divided by T, and this is Curie's law for paramagnetism. So, what we have learnt is that you do these calculations when you apply a magnetic field, the J levels is split, we are working within Russel-Saunders coupling, and once that happens, you apply a magnetic field, different Jz get populated differently because those levels are split, and that leads to this paramagnetism and Curie's law. So, susceptibility goes as C over T. Experimentally, if there are n atoms in a solid, I will have paramagnetic susceptibility per unit volume would be n times mu b square p square over 3 kBt. And experimentally what you check is, after measuring this, what effective magneton number comes out to be. So, I would request you to check the table for rare earth ions in Kittel, where theoretical and experimental P are compared. Okay, and once you do that, you will find that the match between theoretical and experimental P is excellent. And again, for rare earth ions. So, we have explained how these things work. Again, keep in mind that this has been done using the fact that all the magnetic behavior comes from the atoms. We have not taken care of any moving electrons or electrons that may be moving in the band. So, this is purely on the basis of what ions contribute to magnetism. So, that is explained. I need to explain one more thing beyond that, is that when you look at the table for iron group ions. So, you go beyond this, the rare earth ions, and go look at the iron group ions, which will be Fe2 plus, Fe3 plus, cobalt 2 plus, manganese 2 plus, and so on. Here you find that P experimental does not match well with GL root J, J plus 1, but rather it matches with 2 root S, S plus 1. So, we need to explain that, and that will be the end of this lecture. What this implies is that instead of total angular momentum J, it is the total spin that is giving rise to the magnetism in these systems. So, let us write that. In iron group, it is not J, but S that gives the magnetic response. Gs is 2. So, that is why the 2 is coming. So, somehow L does not play a role, and we will now explain why that happened, and this is known as the phenomena of quenching of orbital angular momentum. So, recall when I wrote this Hamiltonian, I had H equals H 0, which depended only on the R magnitude, plus C L dot S plus the magnetic term, right. So, let me write this as mu B G L J dot B plus that square term. We had neglected the non-central part of V effective. And I had said earlier that this is very small. So, this is much smaller than anything else. Center field approximation is good. So, we can neglect that. However, in a crystal environment, this extra part is large, because now an atom is surrounded by other atoms. So, if I make a picture, I have an atom, and when it was alone, everything was spherically symmetric. Now, however, in a crystal environment, I have this atom surrounded by other atoms. So, the potential may not be spherically symmetric, it may have some sort of a non-symmetric part. So, my Hamiltonian now is H 0 plus this delta V non-symmetric plus C L dot S plus mu B G L J dot B. Although I can write the Hamiltonian in this manner, what it assumes is, it assumes that Lz plus Sz give a good quantum number, or even before that, one step backward, Lz can be specified. And now I will show you that this cannot be done. If that cannot be done, then there is a problem. I cannot have this L dot S coupling to start with, because L is not a good quantum number. So, only thing that comes into play is capital S. So, let us see the example that Kittel takes is in this tetragonal lattice, in which the potential V is delta V non-central is some constant C 1 x square plus C 2 y square minus C 1 plus C 2 z square. So, even before I apply that C L dot S perturbation, I need to apply this perturbation, and this perturbation is bigger than C L dot S. So, before applying L dot S coupling, I need to apply that. In that case, if I get proper Lz, I can apply L dot S coupling, otherwise I cannot, my basis will change. So, when I apply a field like V equals C 1 x square plus C 2 y square minus C 1 plus C 2 z square, remember what I started with. I started with H 0, which had these levels n, L, m. L was some 0, 1, 2 and so on. ML was minus L to L, and all these levels were degenerate. And this is because we are in a central potential. Now, what this delta V non-central lifts this degeneracy. So, if I take a p orbital, I have n 1 minus 1, n 1 0 and n 1 1 all degenerate. You apply degenerate perturbation theory, apply V non-central, and you start mixing these states. For example, the example that Kittel takes is you make a state x r, which is the function of r, which is a mixture of n 1 minus 1 plus n 1 1. You make a state y r r, which is a mixture of n 1 minus 1 minus n 1 1, and z r of course is n 1 0. Important thing is that if I take Lz of this x r r, it will come out to be 0, because it is a mixture of plus 1 and minus 1 state, and so does expectation value of Ly, and anyway Lz is 0. So, once this perturbation mixes these states, the L becomes 0. This means expectation value of L will be 0. If that is the case, the only quantity that is left to give magnetic moment is S. So, you end up having J equals S and G square root of J plus 1 goes to 2 square root of S plus 1. So, this non-central part lifts the degeneracy, mixes states in such a way that L part becomes 0, and the only contribution that comes to magnetic moment is from S, and therefore, you have this quenching, and P therefore becomes 2 square root of S plus 1. If the crystal field was not strong or not stronger than L dot S, one would still go and get the result which we had earlier. But if this is stronger than L dot S coupling, then it already splits the levels, and there can be no good L dot S coupling and J states. So, that is the explanation for that. With this, let me now conclude my lecture. So, we have considered L plus Gs S dot B term, and calculated paramagnetic susceptibility for ions. And then we have shown that when strong crystal field is there, it gives L to be 0. So, J equals S, and this quenching of orbital angular momentum gives J equals S. Thank you.